This is a very exciting week because this week we get to talk about Bell's theorem. And the reason that this is exciting is because, okay, we are going to explain Bell's theorem as a no-go theorem for ontological models satisfying, local causality. And we'll explain what all of these things mean. But then we will be able to use this to pivot into something that's underappreciated about Bell's experiment, which is an argument due to Arthur Fine back in like 1982, where basically there's this famous Clauser, Horne, Simony, Holt scenario where Alice and Bob each have two measurement inputs and two outputs. And what Arthur Fine does there is he says, listen, these violations of Bell inequalities, what are these Bell inequalities? They're precisely the conditions for the existence of a joint probability distribution. So this is another, so far we've been talking about classical explanations for the Born rule coming from these ontological models. And what Arthur Fine says is like, hey, listen, actually this is the same thing as just having a joint probability distribution over the random variables corresponding to your measurement outcomes. So we'll make it all very precise, but then this ties in later to contextuality. So maybe just to, in short a little bit, what we have is you've got Bell. And for us, we've talked about Bell as these, or we will talk about it as a local LHVM or ontological model. I'm sort of using those interchangeably. And then these Bell inequalities are if and only if you have a joint probability distribution. This is Fine's theorem, and I think it's a very fundamental theorem. So today we're talking all about Bell's theorem in general. So anyway, I think that this point of view is very nice. So I've done some work on this, and it ties in with there's some very geometrical elements that come with this. So anyway, we'll get to it. One thing that I really want to make clear is that we will also do this presentation of Bell's theorem as there's these local hidden variables, and then you define this thing called a CHSH quantity or inequality, and then you will show, okay, well, quantum mechanics violates this, but local hidden variables have to satisfy it. One thing that's not clear is where that inequality comes from. It's very sort of just, hey, you have these correlations and these correlations and these, you sum them and you subtract them, and it's like, okay, it's kind of an awkward, it seems ad hoc when you first see it. That's how I felt. I will sort of reiterate that the thing about Fine's theorem is that there's a precise condition, a systematic way to derive Bell inequalities, and they're coming precisely from this notion of the conditions for a patch of marginal distributions, empirical distributions that Alice and Bob get for different measurement settings. How do you glue these to a joint probability distribution? That's precisely what the CHSH inequalities are, actually. And so we will get that. We will do the standard presentation later on in the week. Hopefully we'll be able to get to Fine's presentation of this result. Okay, so first we are going to, another thing that I'll just add to that in terms of motivation is I think one thing that I'm trying to drive at in this course is that, people use Fine's theorem, or sorry, Bell's theorem rather, to say like, okay, quantum mechanics is non-local. What they really mean is that we postulate a model, a local ontological model, and we show that quantum mechanics, or that these types of models disagree with quantum mechanics. Therefore, there is no local ontological model consistent with the predictions of quantum mechanics, and we use the shorthand quantum mechanics is non-local for that long statement. That's important takeaway, I think. Okay, so we have first sort of condition that we want to talk about, which is local common causes. So the picture is pretty straightforward. So let's draw a picture. We have regions A, which I will just condense to a point A, a point B. And these things have backwards light cones. And the basic physical sort of postulate that we're going to, there's two of these actually, but one of them that's coming from this sort of causal structure is that it's okay for A and B to be correlated in some ways. Of course, there are many different types of physical variables that are correlated, but what is typically assumed is that in these types of models is that to the extent that A and B are correlated, it's because there was some, in their joint past, there was some region of overlap in space-time, and there's some lambda, so say that this is region C, there's lambda in lambda C, so these are a set of ontic states. To the extent that A and B share some sort of correlations, it's precisely because there is a physical state in their common past which is responsible for those correlations in the future. Yeah, this is just sort of giving the intuition. Ultimately, everything will come down to specifying. So an ontological model is going to consist of a triple, right? So we have this ontic state, these set of lambdas. We will leave that as general as possible. Second, there is this set of preparations, these probability distributions, and then a set of indicator functions. So there's three different types of ingredients that go into an ontological model. And when we look at these particular sort of, when we impose these constraints, like an ontological model is local or an ontological model is non-contextual, it corresponds to a very specific constraint within the sets of functions that we have available to us. So that's precisely what we'll get to. So let's say that we have an experimental scenario, a bipartite scenario, say. So we have regions A and B. Let's just call those RA, RB. And we assume that Alice and Bob are space-like separated observers, and they're going to perform measurement, a measurement procedure that I'll just denote like this, which is to say that this is a measurement procedure in which Alice performs the measurement procedure X in region A, and Bob performs the measurement procedure Y in region B, yielding outcomes RS. So upon performing X, Alice gets, this is supposed to be an R with some probability, and Bob gets S with some probability, or given together, there's some joint probability. And these R's and S's are going to be, I think I can, for this original just sort of description, we'll keep it to +1, -1, because later on we'll consider these local qubit measurements to derive Bell's theorem. So let's just go with ± 1 for now. And so in the corresponding ontological model, what do we have? The ontological model, we have a set of lambdas. The lambdas are precisely going to be the physical variables, the ontic variables, which specify the physical state in their common past. In this region C, I'll drop the subscript C. We have this P given P like this. Sorry, actually, I want to maybe leave this a little bit more general for right now. Okay, my apologies. Let's make this a little bit more general, and then we'll see how the assumptions that you were talking about come in. I think that that will be a more instructive way to do it. So in general, we have that the joint probability distribution of interest, we have those lambdas, and okay, sorry, this is why. So when we perform this experiment, this bipartite experiment with this measurement procedure and these outcomes, for some possible preparation, we have that the empirical probabilities are of this form. And m is just x, comma, y. These are our empirical . So I should really state this first. Okay, so these are essentially the things that will come from the Born rule later on. Now it's fair to go on to the ontological description. We want to reproduce these empirical probabilities using a local ontological model. So first, we have the local ontological model. What is that going to consist of? Let's first start with this joint distribution, R, S, and lambda, given a preparation x, y. I'm going to use the chain rule of probability theory to just decompose this. This is P of R, or let's go with lambda first. P of lambda given P of x, y. P of R given P, comma x, comma y, comma lambda. And P of S given P, comma x, y, lambda, s. So we've used it a couple of times. Basically, I'm just, for every one, I have the original conditioning statement, and then the subsequent ones in the chain, I also add the conditional on this one. So it goes like this. Now, we have two assumptions that we want to go through. Okay, so I remember asking this in one of the earlier lectures. So some of these distributions sort of don't accommodate a sort of classical set of assumptions. Like if I write these down, some of them seem to violate causality. So like, for example, this one. So one of the assumptions we will make is precisely that P of lambda conditional on P should be independent of x and y. So I'll explain this in a second. P of lambda. Okay, so can anyone give a couple of reasons why we might want to make this assumption?
So lambda is the event in the past.
Yeah.
Alice and Bob are measuring in the future. It should be.
Yes, and there's a sort of converse way to think about this as well. That if you have a probability of lambda given p, comma x, comma y, by Bayes' rule, you also would have the following. This thing would be proportional to something like x, y given p proportional to p of lambda p. And so what is this saying to me? So I'm basically using Bayes' rule to invert this thing. And what is this going to tell me? That, that the probability of some measurement settings could depend on lambda. So you're saying that your x and y are not statistically independent from lambda. This is sort of, and usually we assume that this is the case. This is sort of just the reverse of what you're looking at. We should have that Alice and Bob can independently choose their measurement settings in the future. So this, I believe, is called measurement independence. So the next one. Okay, so this is, we've narrowed down this guy, which we've restricted this. And now we also have these, which are part of my indicator function. Now, any idea how I would go about simplifying these? Yeah?
Question to the first assumption.
Yep.
Why does this proportionality tell us that this should be independent of x and y?
Well, what I'm saying is that if this conditional is not independent of x and y, in principle, what you would be saying is that there exists a probability for x and y given some lambda. You would expect that this should be unconditional, like your choice of x and y. Okay, and then this one is factorizability. So this one is going to go by these two statements, or just p of, so let's start with this one first. P of r given p comma x comma y comma lambda. Well, we already argued previously that in a ontological model that that given lambda, that the r should be independent of p. There was this argument that the lambdas are a complete physical specification of the physical state. So once you know what lambda is, the fact that there was a preparation that preceded that is it's independent of this. So we have, at first, we have this given x, y, lambda. And then I think that we see that there's an additional assumption that we might want to make, which is precisely this causal assumption, which is that r should be independent of y, which is Bob's measurement choice. Seems reasonable? Okay, similarly, we have p of s given p, x, y, lambda, and in this case, we also picked up an extra factor of s. This should also, using the, through a similar analysis, r. Through a similar reasoning, we should also have it be independent of p, x, and r. Y comma lambda. So in other words, conditional on the complete specification of the ontic state lambda in their joint past, the statistics of Bob or Alice is independent of the other's measurement choice and outcome. So then we have, given these conditions, we can start from this joint distribution that's suitably simplified, and we say that a local ontological model matches the empirical predictions if you have these equal to precisely P of R S given P comma X comma Y. It's going to be equal to some integral over lambda d lambda P of lambda P of R given X lambda P of S given Y lambda. Okay, so this is precisely the form that we want. And our next step will be, in Bell's theorem, is to show that when the left-hand side comes from some empirical probabilities in quantum mechanics, the right-hand side cannot reproduce these. First, I want to make a slight comment on the form of this. So I just want to take a quick comment to the form of this suggests that certain equations are satisfied. And we're going to see that these equations show up again and again, which is this idea that I can do the following thing. I can marginalize over one of these set of outcomes. So basically average over one of the set of outcomes. Say I take the first one for Alice, by which I mean I sum over Bob's outcomes of P of RS. And to make life easy, I'm going to suppress the dependence on P, capital P, the preparation, X, Y, sorry, this is here. The right-hand side is just going to be me rewriting this with an additional sum. So I have the sum and the integral will commute with each other. So I have lambda d lambda P of lambda P of R given X lambda sum S P of S given Y lambda. This is a probability distribution over the outcomes S. So in particular, this thing equals to 1. And what we get is that this whole thing equals some, integral over lambda d lambda P of lambda P of R given X lambda, which is independent of the measurement setting of Bob. So we can define this thing to be just equal to P of X given, and now I'm just going to be, so there's also the P here, so this is P of R rather, given X. And so what we refer to as the principle of non-signaling is precisely that if I have these empirical probabilities defined in a bipartite sort of measurement scenario or a multipartite one, and I average over one of the set of outcomes, then through that averaging, the marginal distribution, the averaged distribution, no longer cares about what the other measurement setting was. What this is saying is basically, if you think of it in terms of the quantum case, which actually also satisfies non-signaling, when you do this partial trace over what Bob is doing, the reduced state that Alice sees is independent of what Bob does. So this is also satisfied in the classical case. It's also satisfied in quantum theory, and in fact, you can define more general theories than quantum theory, which still satisfy non-signaling. The sort of importance of non-signaling is that if you have a theory that satisfies this, then in some sense you are maintaining consistency with relativity at like an empirical level, because you're saying essentially that the distribution of outcomes that Alice sees depends not at all on what Bob does. If that were not the case, then you could conjure up some sort of scenarios where the distribution does change as Bob varies his measurement settings, and you could use that to signal to Alice or communicate between them. So this is sort of a weakening, or a little bit of a weakening of Bell's condition of this local causal sort of structure, to just saying at the empirical level, we don't see any changes in the probability distributions as the other parties vary their parameters or measurement settings.
How do you call the set O with R and S?
Yeah, sorry, I just used the notation for the set of outcomes. What about that?
Then it confuses me that P of RS, depending on X, Y, because you said we don't need the preparation anymore.
I didn't say, sorry, I didn't mean that we don't need it anymore. I said I'm going to suppress the notation. Sorry, yeah, it was just me being expedient and lazy, not that it doesn't matter. It absolutely will matter because, you know, if you think of it in the quantum case again, this is a particular density matrix that corresponds to a preparation, and the reduced density matrix will depend on, you know, on what density matrix you started with in general.
Is that right? That it could also depend on lambda, but that's not on P?
It could depend on, in this setting, it can still depend on P. It can depend on P regardless.
Because with the same reasoning where you just leave out the preparation and that the factorability, I think that preparation and the state lambda is like interchangeable. Either you...
No, the preparation is a particular procedure which puts lambda in one of several states with some probability. So the preparation determines specifically or precisely which function I put here. I mean, if you think of it like this could be a Gaussian, it could be a different type of distribution, and this is determined by the preparation. Is that okay? Or, I mean, I think it's maybe a subtle point, so we can linger on it a little bit.
So is lambda in some sense less information than the preparation, but deterministic in that sense that you don't have probability distribution, but a definite state?
I think that that's, hold on, let me think. So you're asking if are you asking if you can get rid of P somewhere? I think that this is...
Maybe, what's the reason again where we can get rid of P there?
The reason that we can get rid of P here, or that we had argued previously, is that what a preparation does is it elicits a particular sort of state lambda with some probability. But the idea is that if you knew what lambda is, then you no longer really care about the preparation.
Okay, so if we have the dependence on the preparation and lambda, we can always...
Yes, that's exactly, in ontological models, contingent on lambda, you can erase the preparation.
Not the other way around. So we cannot get...
So if you know preparation, it doesn't necessarily tell you lambda. Now we will go to the Clauser-Horne Simony Holt scenario. So there's sort of a, I will not use Bell's original argument. I think that it's a little bit less clean than just using this one. Clauser-Horne. or just CHSH. And the picture to this one is going to go something like this. In operational terms, you just have Alice, Bob. They each have two different inputs, x1, x2, say. These inputs correspond to two different local measurement procedures. And y1, y2. We'll see that this corresponds to something like Alice chooses to measure in one basis or another in the quantum side. Bob chooses to measure in one basis or another. And the outcomes are going to be +1 or -1 with some probability. Correspondingly, we have that, let's see, I guess do I want to go to the quantum description right away? No, okay, I don't want to do that right away. What I first want to do is to derive this inequality, and from there we can go ahead and show that quantum mechanics violates it. Is there anything else I want to say about this? No, I think that that's okay. So we have the following empirical probabilities. I guess, I don't know, you want to call this a proposition or something. There's a inequality, and let's see if I get the notation correct. We have that this inequality E x1, y1 plus E of x1, y2 plus E of x2, y1 minus E of x2, y2. So this is our expression. Let's call this S. And we say that, and E of xi, yi, yj rather. So let's make this a little bit easier. E of xi, yj is going to be defined as sum over Rs of, and these can be both plus or minus 1, and this is, R times S times P of Rs given xy. Again, we're suppressing the preparation for the time being. And the inequality is that S is less than or equal to 2. Okay, so let's just unpack this very quickly. We define this thing. This thing is a correlation. And I think I will bring this back down. One thing I want to point out is that as opposed to EPR, which sort of had this argument about correlations, but they never really put it to a test. What I think that is very significant about what Bell does is that this inequality is based only on empirical data, so you can put it to a test. So previously, Einstein, Podolsky, Rosen, these types of arguments, they never wrote down something just purely in terms of empirical frequencies that you could actually go out and test. So here, we define the correlations. What are these? Basically, I have two variables, R and S, and you average over their joint expectation. So these things in particular can be between plus and minus 1. What we want to do now is go ahead and show this inequality. I think that probably one thing that we want to define first is so. I'm going to first define this guy. So this is the proof. Let me write that here, just so we're. And I define this guy. He will be equal to sum over R times P of R given X and lambda. So this guy will depend on lambda. And I have by of lambda equals s, p of s given y comma lambda. And now we can write down the whole sort of expression for, and both of these are in -1 to 1. So now if I write down any particular e of xy, that's going to look something like integral d lambda p of lambda ax of lambda by of lambda. The reason being precisely that when I write this, maybe I skipped a step here, sorry about that. When I write this thing in terms of the ontological model over here, when I have the sum over R and S, I can look at the sum over R independently, I can look at the sum over S independently. So this piece will give me the A, this piece will give me the B, and both will depend on lambda. So I have something just like this for each possible e of xy. So then the total expression is something like S is equal to lambda p lambda, and then we have we have a very long expression that I'm not wanting to write. ax1, the lambda suppression, I will suppress lambda just to make life easy for me. b1 plus ax1 by2 plus ax2 by1 minus ax2 by2. We can simplify this somewhat. ax1 times bx1 plus bx2 plus ax2 bx1 minus bx2. Then, when you take the absolute value of this thing, what's going to happen? So, a couple of things are going to happen. First, I should mention, again, this is between +1 and -1. This is also between +1 and -1. This one is between, between -2 and 2. They could both be -1. This is also between -2 and 2. So if I take the absolute value of this thing, using those bounds and the triangle inequality, so how much do I want to do? Look at that. Let's see. Let me write down the expression and see if you guys believe me. D lambda, P of lambda, this is positive. And then we have y1 plus by2 plus the absolute value, let me move this here, plus by1 minus by2. So then we use the fact that this thing is at least between -2 and 2, so that the expectation value itself is actually less than or equal to 2. This is also less than or equal to 2. Yes. So we have that this whole thing is less than or equal to d lambda p of lambda times 2, which just equals to 2. So we have okay, so can anyone recall, for people who have seen this, what the quantum violation, how the argument sort of goes, roughly? I mean, you're not expected to know. This is what the course is for, right? I'm just wondering if people have a flavor of how it goes. Mm-hmm. Okay, very good. So let's take our state to be okay, so what do I mean by this? So we are taking a Hilbert space, which is C2 tensor C2, and we take the following basis, the computational basis, which is x tensor y, where x and y are in 0, 1. So this is a particular vector in there. It's normalized. This is sometimes called the Bell state. Okay, very good. So in this sort of operational picture, this would be our preparation, right? And okay, so what's the next ingredient that we need? So we'll also want to define a measurement procedure. Interesting to note that not any measurement procedure will work to get the violation. You have to sort of, so okay, let me write this down first. So let's say that Alice measures has access to the following measurements. These are going to correspond to the x1 and x2 that I had written down previously. So this is going to be the Pauli Z. This is acting on one of the tensor factors. And just for completeness, this is 0, 1, 1, sorry, completely wrong. 1, 0, 0, minus 1. And let's let A2 be equal to sigma x, I guess I took it to be. So these are both Hermitian. They both have eigenvalues plus or minus 1. So they fit within this setup of the CHSH inequality. Okay, so this is Alice's side. On Bob's side, we have to do something a little bit different. So on Bob's side, we have yes. Okay, so what these are, so in the block sphere, so I don't know, let's just give a quick geometric picture here. So for either of their individual qubits, we have first that this is the sigma x-axis, sigma z. So Alice's measurements are precisely this and this. Maybe worthwhile to distinguish. And then Bob's measurements are going to be, ooh, well, this is one of them for sure. And then I have to think about the other one. So it's sigma x minus sigma z. So it's like this. I will just note that if I had picked Bob's measurements to also lie along the Cartesian axes here, I would not get a Bell violation. You kind of need this twist. You need this like non-stabilizer state for people who know the jargon. Otherwise, yeah, you just won't get the this will give you the maximum violation, and then you will, if you pick a basis that's maybe a little bit tilted relative to this one, you can still violate it, but this one will give you the maximum violation. And if you align with the axes completely, you won't get any violation.
So you need one stabilizer state and one that's not stabilizer, or?
It's not exactly like that, because it could have been the case that one of Alice's measurements are stabilizer and the other is not, and then the same for Bob. In this picture, yeah, you need at least two measurements in the setup, I think, to be non-stabilizer. Don't quote me on that, but in my experience, that's the way that it is. I think it's provable, but for sure, in this way of doing it, these both need to be non-stabilizer. Another way of doing it is that Alice has one stabilizer, one not. Bob has one stabilizer and also one not. That'll also work, I believe. Boom, boom, boom. Okay, so now we are actually going to compute these E functions, the ones that come from quantum mechanics, precisely with these preparations and these measurements. So in our picture, this E function, or in the quantum case, EI yj that we defined before, what is this thing going to be? This is phi of AI tensor Bj. We can go ahead and compute these. I do want to make a connection to, I would like to make a connection to the way that we wrote these down before as being the expectation values of something. And in that case, let's see, AI tensor Bj, this will be, there's a spectral decomposition for this one as well as for this. So I will write this as pi, maybe I write this pi A plus, so just drop these indices to make things a little bit easier, minus pi A minus pi B plus minus pi B minus, so pi A tensor pi B. In fact, this is a sum over RS in plus 1 minus 1. So they could both be positive. So then I just have this factor RS here. Maybe I can squeeze it in here. RS. R is for this one, so it's plus when this is plus, minus, minus. So then the expectation value of this thing is precisely I'll just keep it as xy again, is precisely going to be equal to RS pi A R pi B S so we have some RS pi A R tensor pi B S. Can anyone interpret what these inside the sum look like? I don't know if that's legible. Yeah, this bracket.
Das ist die Probability of Alice measuring.
I didn't write, but say she's measuring one of her measurements and Bob measuring one of his measurements and getting outcome RS. Yeah, precisely. So this is precisely the empirical probability. So P of RS given our preparation phi and some inputs, which we will say were x, y, a, x, r, b, y, s. Okay, so this is precisely going to give us the expression that we had before, because then we just have that E of xy is sum rs rs p of rs given phi comma x y, which is what we expected. Now, we can compute each of these explicitly. We have an explicit form for this, and then we know exactly what the measurement operators are, but I will save us the hassle of doing this. So let's say E11, just to save a little bit of notation. This one is going to be equal to, well, maybe we should at least do one of these just to see how it works. So phi of, well, I can just go back to this picture. So I have sigma z tensor sigma, sigma x plus sigma z over the square root of 2. So we have sigma z tensor sigma x, maybe a square root of 2 here, plus 1 over square root of 2 sigma z tensor sigma z. I will just write down the answer and then give you guys the way that I compute it, but it's not within scope to compute it like this right now. So this one will be 0, and this one will be This one will be 1. So this is 1 over the square root of 2. So for those who are not familiar, this thing is called a stabilizer state. It has an expansion in this thing called the block basis, and its stabilizers are precisely sigma zz, sigma xx, and sigma y, sigma y, sigma y. So anything that's not in the set that I just mentioned it's got an expectation value that's 0. And anything that is in the set that I mentioned has an expectation value of +1 or -1. And in this case, it's +1. You could compute it more directly from the operator and this here, but I'm just not going to, I guess. Okay, so what about the rest of them? Okay, sigma 1, 2, then I have sigma z, and I think this is going to be then -1/2. Oh, I hope I got those minus signs right. Okay, so based on that same calculation, you're going to get a sigma z, sigma x again, but then a minus sigma z, sigma z. So this is going to be -1 over square root of 2. E of 2, 1 is going to have sigma x. So you're going to have a sigma x here, and then a sigma x. That'll be a +1. And then sigma x, sigma z on the second. That'll be a 0. So this is again square root of 1 over 2. And then sigma 2, sigma 2. There needs to be a minus that shows up here somewhere. So it will be sigma x, sigma x, sigma x, sigma x. And then I do this one, sigma x, sigma x. So I get +1 again. Oh, okay. So I did choose something minus that should have. Okay, I think it's actually, say I chose this one. If I chose this one, let's go through. I don't think it changes anything there. Then all I need to look at is the number 2 one. So here, sigma z, sigma x is still 0. Sigma z is now plus. This one is still plus. Now this one will be 1 over square root of 2. Okay, I need it to be in this order. Actually, it doesn't matter if I chose another CHSH inequality. There's 8 altogether. You can permute the minus sign through appropriately. And I could have gotten a violation using the set that I picked, but just to stay consistent, you get the minus sign here. So now what is this S going to give us? It is E of 1, 1 plus E of 1, 2 plus E of 2, 1 minus E of 2, 2. And so S is equal to 1 over square root of 2, 1 over square root of 2. Equals 2 over square root of 2. Sorry, no, 4 over the square root of 2. Which is precisely 2 square root of 2. Okay, which is, so S quantum, let's put it as quantum, S quantum greater than S classical, which had to be less than or equal to 2. Okay, so that is a demonstration of Bell's theorem, which is nice. Have you guys seen that demonstration before? Maybe. If you've seen one, it's probably been that one. Okay, actually, we are running up close to the end of the time. One thing I did want to show was that return to the non-signaling principle. And the idea was just to show you that if I have a projector like so, with two different outcomes, which is given by pi of x r tensor pi of ys, then for any given bipartite state, so this is a bipartite operator, and then I have, say, some rho, which is a density operator on my, say, HA times HB, then I always have the following equations that are satisfied. So if I have P of Rs given rho and we say that this is x, y, this is given by trace rho pi x r pi y s. Then the non-signaling conditions are always satisfied for the Born rule probabilities that are of this form. In particular, just take one of these, sum over r, P of r s rho x y. We sum over r in the trace, rho pi x r y s. You use the fact that I can bring the sum inside of here, and it will not touch the second tensor factor. So I have trace rho sum r pi x y tensor pi ys, and it's so just to rewrite that piece, we get trace rho sum r pi x r tensor pi ys. This piece, maybe I didn't write it down explicitly. It's said in the notes that each of these pieces themselves are part of these are projectors coming from some PVM, which is just to say that they sum to the identity. So I have identity on the first tensor factor tensored with pi ys. Now we see that actually this is equivalent to taking the partial trace over the first tensor factor, but in particular, we don't actually need that. What we know is that whatever this is, it doesn't depend on x or y anymore. So this is precisely s given rho comma y. So the Born rule, whenever we have these sort of bipartite or multipartite situations, they also satisfy the non-signaling principle. And this is how you sort of, even though we have this violation, and this violation is supposed to, this bound is coming from locally causal models. In particular, they're sort of motivated by the causal structure of special relativity. So does this violation mean that we sort of have this superluminal signaling? And no, because at an operational level, quantum mechanics still has that the operational or empirical probabilities are independent of, so what Bob sees in this case is the probabilities that Bob sees are still independent of what Alice does. So everything is okay. Okay, very nice. So we got to what I wanted to talk about. Next time, we will start making connections to contextuality. We'll see. I mean, it seems unrelated, but we'll have to pass through a little bit of joint probability, stuff about joint probabilities, Fine's theorem, and then we'll make the connection between Bell's theorem, Fine's theorem, and contextuality. Okay, so exciting. Next class, there will be plenty to talk about.